So here is a game with many players. It's in fact not just many players, but infinitely many, a continuum of players. The game is a game that comes from the transportation domain. We call it the traffic game. And imagine the following network of 4 locations. The many drivers all start in location 1 and want to go to location B, and they can go through either the left or the right. And their choice of strategies are very simple, and their preferences are also fairly straightforward. They're all defined by the delay they incur. But the delay is constructed in the following way. If they go down the right, then the first leg of the trip, the delay there depends on how many people chose that route. So call the fraction of the drivers who drove that way f. F is between 0 and 1, and that is the delay. The higher the fraction, the longer the delay. And the second leg is more straightforward. It's a fixed delay of 1.2 hours. Okay. The situation on the left is constructed similarly. It is first a fixed delay of 1.2, and then a variable delay, again as a function of the players who decided to go on the right, in this case 1 minus that fraction. Okay, how do we reason about such a game? Well, first let's set it up as a formal game. We have the set of players, n in this case, as we said, is infinite. It's all the rational numbers between 0 and 1. The actions are for each of these many players is very simple: go left or go right. And the payoffs will be a function of the delay. They will be a minus the delay. The delay will be a function of the fraction. So let's set it up formally. The delay u sub I of the players will be, just as soon as I find my cursor here, the delay will be u sub I will be a function of the action AI chose by the player, left or right, and that fraction of players who decided to go right. Notice that we're making an assumption here of there being many players. So since there are infinitely many players, the action of the one player won't impact that fraction that chooses left or right. So what's the payoff? The payoff is simply the sum of the delays, or minus the sum of the delays. So in the case of going left, it is a fixed delay of 1.2 and then a variable delay y minus f. And similarly for the act of going right. Now that we have it set up, we can reason about it. Let's reason about it and ask very simply, when is it best to go left? Well, it's best to go left if the delay there is less. And the delay, we just copy the expression we saw before. That's the delay of going left, and this is the delay of going right. And if you just rearrange the term, you see that going left is always the best thing to do if at least half the players are going right. Similarly, a very simple analysis shows you that if at most half the players are going right, that is at least half are going left, then the unique best response is to go right. Well, with that, we're in a position to show the equilibrium of this game. Let's think of 3 different possibilities corresponding to what fraction of players are going right. Strictly greater than half of the players are going right, then as we've just seen, going left is the unique best response. Well, that means that no one is going right, inconsistent with the assumption that at least half are going right. So this is an inconsistent situation. By similar analysis, you can show that it can't be that strictly less than half are going right. Well, that means that the only possibility is that we split the traffic, that exactly half are going left and half are going right, and this is indeed the unique equilibrium. the delay that everybody experiences is 1.2 plus a half, which is 1.7, and this is seems very straightforward. Indeed it is, until we introduce the following wrinkle. And this brings us to something called the Braess Paradox, after the mathematician Braess, who in 1968 introduced this example in the journal called Transportation Science. Imagine that the government has decided to do well with the population and built a new highway going uniquely from right to left, very fast, a very short delay of a mere 0.1 hours. Now agents have an additional option. They can, as before, go strictly down the right or strictly down the left, or if they so choose, they can snake around and take this route. Surely more options are always better. Well, let's see. What are the payoffs to the agents who take these options? Again, we have three options. The first one as before. If you go down the right, and we will, just to be explicit about it, break it down. You go down the upper right, and then the lower right, and the sum of your delay is this delay. No change to the strictly going down the left. As far as snaking around goes, well, you incur the first variable delay of going down the upper right, then the very low delay of 0.1 of going across, and then again the variable delay of going down the bottom left. And now notice something interesting. Notice that in fact the snaking around is better than going either straight down left or straight down right. And why is that? Well, let's look at going down right. We have this variable delay which is common to this snaking around, and then we have the fixed delay of 1.2 various this variable delay of this. Now what could that be? Well, FL2 will be at most 1, and therefore this variable component will be at most 1.1, which is less than 1.2. And therefore snaking around is better than going down right. And by a similar analysis you show that it's better than going down left. That brings us to the very unambiguous situation where everybody prefers to snake around. It's a dominant strategy for them. Well, lo and behold, what is their delay? Well, if everybody goes down the right at first, that's a delay of 1. Plus minus 1, plus 0.1 for going across, plus, since everybody's going down the bottom left, a delay of 1 for a total delay of 2.1, which is of course worse than the delay that we had of 1.7. This is might seem as a theoretical curiosity. In fact, there's anecdotal evidence that you see it in real life. There's a famous example in Manhattan where 42nd Street was closed down for construction, and the claim is traffic eased in the city. Be that as it may, it's very clear that negative externalities, as they're called, create very complicated game situations. An externality is a situation very common where my action has a cost or a benefit to others in the game with no control over them. In this case, my deciding to take a particular route created additional congestion to other players. And this particular game is constructed in such a way that the negative externality is substantially exacerbated by the addition of this new, apparently benign link. That's the Braess paradox.